In this video of the College Algebra Final Exam Review, we're going to start looking at the linear equation problems. And I certainly hope that this is a review. However, some of the questions are asked in such a way that you might need a little bit of help getting started with them again. So in part A of this particular question, we're being asked to find an equation for the line labeled L1 in this figure. And if the instructions aren't given to you that we're looking specifically for a slope-intercept form, mx plus b, then you might be a bit confused. But this is my chance to remind you that that's exactly what we're looking for. If the solution is supposed to be in the form y equals mx plus b, the slope-intercept form, well, it's super easy to identify the intercept, and it's fairly easy to calculate the slope. Just remember that you've got to pick 2 points, any 2 points that are on nice lattice marks, so nice intersections of the grid, and then you can count the rise and the run. Since this is a linear equation, those rise and run values will be the same. And in this case, we've got a rise of 4, run of 1, which is the fraction 4 over 1 reduced to 4. And our intercept is 3, so we'll call this equation 4x plus 3. Now that we have the slope-intercept form, of course the y-intercept is easy to identify, but we've also got an equation that we can use to identify the x-intercept if we were asked to do so. It doesn't exist on a nice lattice point here, but we could certainly compute that now that we have the equation. Now part B goes on to ask us to write the equation x plus 4y equals 8 in slope-intercept form. So remember, that's this style up here. All we have to do is get the y by itself, or isolate the y. From there, we'll sketch the graph and talk about the relationship between L1 and L2. In this case, when we're asking questions about the relationship, we're essentially asking, are the two lines parallel? Are the two lines perpendicular? Or are the two lines neither perpendicular nor parallel? So that's what we'll answer with that. As far as the equation goes, if we start with x plus 4y equals 8, I think I would move the x value to the right-hand side. So we have 4y equals negative x plus 8. I'll write it in that order since it's most closely related to the slope-intercept form. And then I'll divide both sides by 4. Now keep in mind that everything gets divided by 4, not just the slope and not just the intercept. So as far as our final equation goes, I like negative 1/4 x plus 2. This negative 1 was divided by 4, and this 8 was divided by 4, and we now have our slope-intercept form. With an intercept of 2 and a slope of negative 1/4, that means we would drop 1 and run 4 to reconnect with the graph, or we could rise 1 and run left 4 to reconnect with the graph. And I'll cheat with my straight edge here. And we've got ourselves a nice line that represents that equation. To me, the two lines look like that they are perpendicular to one another, but it's fairly easy to determine that. You should recall that in parallel lines, the slopes of two lines are equal to one another. And in perpendicular lines, slopes are opposite reciprocals of one another. See if I can spell that correctly, reciprocals. And opposite reciprocals means opposite, well, that's either a plus or a minus sign. If one's positive, then the other's negative, and vice versa. And reciprocal means to flip the fraction. So if the slope here is negative 1/4, then the opposite of that would be a positive number. And if we flip the fraction, it would be 4 over 1 instead of 1 over 4. And is that the opposite reciprocal of this up here? Well, certainly. So while they appear perpendicular, we've now confirmed that they are. And we could state that about the relationship here. The relationship between L1 and L2 are that they are perpendicular lines. Now for part C, find an equation for the line which contains this point and is parallel to L1. Well, if we're parallel to L1, just as we had mentioned a minute ago, the slopes must be equal. So in this new line, the slope must be 4, because that's the same as the original slope, and it must contain the point 3, negative 1. In order to write an equation for this, we would probably consider the point-slope formula. And the point-slope formula was the y minus y1 equals m times x minus x1, where x1 and y1 are two values from the coordinate x1, y1. M is also a value. That happens to be the slope of the line. And the letters y and x remain as letters themselves. We need that to generate the equation of the line. So y minus negative 1 equals 4 times x minus 3. Believe it or not, that is an equation for this line. And the instructions here were fairly vague. It said find an equation. Well, we've done that now. This is good. If the question is a bit more specific on the exam, we might want to clean this up a little bit. When you subtract a negative 1, that's plus 1. We can distribute the 4 to eliminate the parentheses. And then also we can add 1 to both sides. And now we have 4x minus 11, and that's an equation in slope-intercept form. So both of those are technically correct. This one is an equation, while this one is the slope-intercept equation of the same line. I would argue that this is a little bit easier to graph because we've used it more often, but either one would be fine. The next example talks about an equation that's written in general form. We call this general form when the x's and the y's are together on one side of the equation with any other constants on the other side. We can determine the x and y intercepts fairly easily and sketch the graph. The other option, of course, is to rewrite this in slope-intercept form. Well, I say that it's easy to graph the two intercepts because, well, they're easy to find, and all we need are 2 points in order to create a line. So I'm going to find the x-intercept first. Recall that the x-intercept is found when y is set equal to 0. So if we take this equation, 2x minus 3 times 0 equals 6, we really only need to solve when 2x is equal to 6, which means that x is equal to 3. So therefore, we have a coordinate at 3, 0. When x is 3, y is 0, and vice versa. When y is 0, x is 3. For the y-intercept, we set x equal to 0, and we do the same thing. 2 times 0 minus 3y equals 6. Well, that would be the same as when just negative 3y is equal to 6. Therefore, y is equal to negative 2, and we've got the coordinate 0, negative 2. When x is 0, y is negative 2, and when y is negative 2, x is 0. We can plot these points, 3, 0, and 0, negative 2, and we can connect them with a line. And we've got a nice sketch of the equation that was provided to us originally. Also, I would argue that we could create the slope-intercept form fairly quickly from this too. We know that the slope is 2/3, the y-intercept is negative 2, and by looking at the graph, we now have the slope-intercept form of the equation, and we didn't actually have to apply any algebra to the original problem to obtain that result. Now, I've already addressed a little bit about parallel and perpendicular lines already. This notion of their descriptions by way of their slopes was addressed just a moment ago, so I won't go over that anymore. Systems of equations were covered in class. We talked about those between Tuesday and Thursday of this week. So if you missed class or you missed the conversation, by all means reach out to me for some clarification. There should be some Math Excel questions that cover this in the most recent review, and if not, then I'll put something together for you to address that a little bit more clearly. So we'll move on to identifying results of composite functions. And this first set of examples comes from determining results of composite functions from tables. So we've got this table of data that's provided to us here, and basically what it says is that if my job is to evaluate f at 2, for example, I look in my x row and find the number 2, And if I would like to find the function result for f at 2, I just look at the row of f, and I see that f of 2 is equal to 1. If I wanted to evaluate g at 5, I run to the number 5 in the x row and jump down to the g row and look for its result. G of 5 is equal to 4. As far as composite functions go, let's recall that we must work from the inside out. And in order to answer this question, I must first evaluate g at 2. So I'm going to start at 2, and I'm going to look at the g result. The result of g at 2 is equal to 0, and it's the result of this g of 2 that becomes the input of the f function on the outside. So f evaluated at g of 2 is the same as f being evaluated at 0, since g of 2 is 0. And now I'll jump to the 0 value in the x row and look at the f result, and I see the result to that is the number 2. If I reverse the order, g evaluated at f of 2, I start with the f function and evaluate it at 2. So that result is 1. So I'll evaluate g at 1 because g evaluated at f of 2 is the same as g evaluated at 1. f of 2 is the same as the number 1. So now g evaluated at 1 is equal to 5, and we can say that g of f of 2 is equal to 5. Now, a question that seemed to catch a few students off guard the last time we asked this on a test is a problem like letter C. This time we're being asked to find the x value necessary so that the composition of functions will equal 2 when we're done. So in a sense we have to work backwards here. And normally we start from the inside and work our way out, but I'm going to start from the outside and work our way in because again we're going backwards here. And I'm asking myself, g evaluated at what number will generate the result 2? Well, if I'm looking for the result in the g row that gives me the answer 2, that must mean that the number 4 was used to generate the result 2 inside of the g function. So I now recognize that g at 4 is equal to 2. Well, if it takes g evaluated at 4 to give me 2, now I would like to know what was the result, or what was the x value placed into f that gives me the result 4. f evaluated at what number equals 4? Well, if I'm looking at the f row, looking for the result 4, turns out it was the number 1 that produced that result. f evaluated at 1 equaled 4. So, if I were going to ask this question, what x value is necessary so that the composition in this order will produce the number 2, I'm going to go with number 1 as my answer. Number 1 is the result. That's the x value that got everything started. And let's just check our work. Does g of f of 1 equal 4? I'm sorry, equal 2? That's what our original question was. Well, let's check. f evaluated at 1 gives us 4. From this 4, we jump to the new x value. 4 evaluated at g gave us 2. So when we work from the inside out, g of f of 1 does equal 2. So I'm satisfied in saying that the solution to this particular question is the x value equal to 1. The composition of functions that we're working on now were covered most recently in Unit 4. So I hope that still sounds familiar. If we consider other composite functions, or questions about composite functions, sometimes we have to identify inner and outer elements, inner and outer functions, in order to create a composition of functions that looks like this, a complicated result. And so the instructions here are saying that this function y can be written as a composition of two other functions. And our job is to find formulas for f and g so that f acts as the outer function while g acts as our inner function, and both, when composed together, will be this function composed. So if I'm looking at this, I think I would say that the outer function f of x is the fourth root of x, because to me I see the fourth root of something is acting as our outer function. I would then say that my inner function, g of x, would have to be 16 minus x, because that is the something that's acting on the inside of our outer function. As we had mentioned in class, that's not necessarily the only answer that works, but we want to avoid the trivial solutions. So it would not be appropriate to say that the outer function is the fourth root of 16 minus x squared, while the inner function is just x. That's no good. That's what we call a trivial function, because we're essentially copying the composite function and calling that one of our inner or outers. An alternative to the first answer that would be considered correct. This is atypical, but it is technically correct. What if we say that the outer function is 16 minus x, the fourth root of 16 minus x? Then we could say that the inner function is simply x squared. Because if I replace this argument with x squared, I would have the original function. Whereas back here, we took 16 minus x and replaced the original argument and got the same thing as well. So technically, either one of those are correct. I would say the answer on the left is more appropriate in this case, more common, definitely. For part B, I think my outer function, well, again, we've got a couple different options here. I like the answer 3 over x for my outer function. Then I can claim that the inner function is 2x plus 1. This way, if I substitute 2x plus 1 in place of this x, I'll end up with 3 over 2x plus 1. There are other non-trivial solutions that would be accepted. If you can think of any and want to double check with me, by all means reach out to me. What we do want to avoid are the trivial solutions. So if you have a non-trivial solution, one that is not trivial, and you'd like to check, please let me know. The last example that I'd like to discuss in this video is about graph movement, and you should recall that the graphs of parent functions can be transformed by using 4 variables. And we sometimes say that the resulting graph y equals is dependent upon the variable a, which multiplies by a function. Within the interior argument of that function, we might have another variable b, another argument, or the argument of the equation is x, with a third variable c, and a fourth variable d. This a value, since it's a product, could be considered as a positive or a negative result, as well as b, positive or negative. And essentially what we're saying is that the multiplication on the exterior or on the interior could affect or change the way a shape appears. The addition of a c or a d value could also change the way the graph appears. These two affect the stretches of a graph, and these two, when added, affect the shifts of a graph. Whereas the negative signs in front of A and B affect the flips of a graph, or reflections. So if I'm looking at this particular question here, y equals 1 minus x to the fourth, I might think of this as y equals negative x to the fourth plus 1, because now that's in order of the format that we discussed originally. This allows me to recognize that my d value is equal to 1, positive. There is an a value here that's equal to negative 1. It's the negative sign that I'm most worried about. And it appears that my parent function is x to the fourth power. There's nothing grouped with that x that's being raised to the fourth power. It's just x to the fourth power. So that's how I know that this negative sign is part of a and not part of b. Had this been written as the quantity of negative x to the fourth power, then we would have had a negative b value. But this is a negative a value, so that tells me that we've got a vertical flip of the parent function, and we've got a d value of positive 1, so that tells me we've got a vertical shift of the function. Now this test question has 3 blank graphs, and that's because the instructions are essentially asking you to draw the parent function first. X to the 4th power behaves much like x to the 2nd power. It looks very much like a parabola. So we could write x to the 4th power first and indicate this as our parent function. Then we would choose the next appropriate transformation, which in this case is going to be the a value, because we're going to apply the transformations in the order of operations. This negative multiplication has to be done before this addition. So to draw negative x to the 4th, I would show the same x to the 4th power, only flipped vertically. And then if we incorporate the vertical shift, now that our order of operations is complete, this graph gets shifted up 1 unit. And this graph here would represent y equals negative x to the 4th plus 1. In our tests prior to this, I suggest that you should be able to complete all transformations on one graph. And if necessary, you can sketch the parent function either lightly or with dotted lines. You can show additional movement on the same set of x and y axes just very lightly, and then make your final answer a little bit more bold. So if you'd like to do that on our test or on this exam, that would be fine too. If you would like to utilize the 3 or 4 empty graphs, that would be okay too. That way you can show your work along the way. In the next video, we'll pick up with Unit 2 and Unit 4 and their discussion of inverse functions, and then we'll see how far we can get along the way with that. Thanks for watching.